In this set of notes, we're going to look at residuals and diagnostics. So after a model has been fit, it's wise to check the model to see how well it fits the data. In linear regression, these diagnostics were built around residuals and the residual sum squares. In logistic regression and all generalized linear models, there are a few different kinds of residuals and thus different equivalents to the residual sum of squares. So just kind of a starting note here, both SAS and R report by default a chi-square test associated with the entire model. This is a likelihood ratio test in the model compared to the intercept-only null model, similar to the overall F test in linear regression. The test is sometimes used to justify the model, however, this is a mistake. And so if you'll remember, we talked about the model utility test before in 681, and really what we were doing in that test is we were looking at a hypothesis test to see whether or not we had evidence that any of the coefficients were non-zero. So just like all models based on inference, the likelihood ratio test is justified under the assumption that the model holds. The only thing one can conclude from a significant overall chi-square test is that if the model is true, some of its coefficients are non-zero. Addressing the validity and stability of a model is a much more complicated and nuanced than a simple test, and here we now turn that to our attention. So we're going to start by looking at residuals. So the first kind of residual we're going to consider is a Pearson residual, and it's based on the idea of subtracting off the mean and dividing by the standard deviation. So the first thing to notice is that there are M covariate patterns, then there are M residuals. So what do we mean by covariate patterns? All right, so what we're going to do to illustrate this is we're going to consider two models. So the first one, in model 1, we're going to have a single quantitative explanatory variable. And in model 2, we're going to have a single binary, or we'll say dichotomous, explanatory variable. Okay, so when we've worked with quantitative variables as our explanatory variable, we know that the explanatory variable can take many, many values. So possible values, let's say that some of our possible values that we see in our explanatory variable are ranging anywhere from 0 to 10. On the other hand, when we have a single dichotomous explanatory variable, we may only have 0 or 1. So when we think about a residual and what a residual does, is we're really talking about comparing our predicted outcome with the observed outcome. And so when we think of the possible covariate patterns, in model 1, we may have lots and lots of values for our quantitative variable with no overlap. Whereas in model 2, we're going to have lots and lots of overlap in the values that our covariate takes. So for example, we might have 100 observations that had 0 for the explanatory variable and 200 that had 1 for the explanatory variable. So in this case, we would only have 2 covariate patterns. In this case, the number of covariate patterns depends on the number of unique xi that we observe. And often when we're working with logistic regression, it's pretty common to have, a covariate, even a single covariate that is dichotomous or categorical. So you will end up with, lots of observations that have the same, set of explanatory variables, but obviously the outcome could be different for those observations. All right, so, and then if we think of the number of covariate patterns, that's going to determine the number of residuals, because I'm still going to have a fitted value, and that fitted value is going to be the same for all the zeros and for all of the ones. So let's let yk denote the number of successes, nk the number of trials, and pi hat k the estimated probability of success for the kth covariate pattern. Then we can define the Pearson's residual as follows. And so notice again, with these we're using a subscript k here because we may not have a different residual for each observation. We're really going to have a different residual for each of the covariate patterns. Now, it may be the case that the number of covariate patterns equals the number of observations, but in the case of model 2 that we have down here, we can see very quickly that the number of covariate patterns is going to be less than the number of observations. Another residual that we could be interested in is the deviance residuals. So we can think of it as the distance from the perfect fit. So that would be a measure of how your logistic regression model deviates from an ideal model that perfectly fits the data. This perfect model is often called the saturated model, and deviance ranges from 0 to infinity. This type of residual is based on the contribution of each point to the likelihood, and so for logistic regression, here is the likelihood, and suppose that we want to compare the likelihood at the MLE and at the observed, this would suggest the following residual called the deviance residual. And I've got a link here where you can read more about the deviance residual. So just to kind of talk about what do we mean by this comparison of the likelihood for a perfect fit versus our fit, let's look at what that would kind of look like. So suppose that I wanted to plot my data. And so here at the bottom we'll have a 0 and then a 1 at the top, and this will denote my response variable. And then for sake of argument, let's just say along the x-axis we have a single quantitative predictor variable. Now when we think of what our observed data is going to look like, is along the x-axis I could take lots and lots of different values, but along the y-axis I'm only going to take a 0 or a 1, a success or a failure. So potential data might look something like this. Now, when we talk about a perfect model fit or a saturated model, what we really mean is we're thinking of something a fit that looks like this. In other words, we're basically just following exactly what the data have. Whereas when we think of our logistic regression or our fitted logistic regression model, we're more likely to see something like this. And so essentially what the deviance is doing is it's comparing the two of these, is one way to think about that. All right. Now, for each of these types of residuals, we can standardize them, but before we do that, we need to discuss what's called the hat matrix. So, you may recall when we looked at leverage in 681, we introduced this idea of leverage, and in the denominator, you saw something that looks like this, and it may have been denoted with a lowercase h instead of an uppercase. And so it ends up that you can do something similar for logistic regression, and where these h values come from is they come what's called the projection matrix or the hat matrix. And for logistic regression, this is how the hat matrix is calculated. So you'll notice that weight matrix is in there as well. Now in your notes, I've included an additional link where you can go and read more about just the hat matrix in general. Ends up the hat matrix is really important in regression. And so it ends up it has some nice properties. Now in logistic regression, it ends up that pi hat sub I does not equal hy. No matrix can satisfy that requirement as it does not produce linear estimates. Now it does have that nice property though in linear regression. It does have some other nice properties though that would be the same as the linear regression projection matrix, and I'll let you kind of look at these on your own if you're interested. So this is kind of just a nice theoretical side note. We don't, even though the hat matrix or the projection matrix is really important and it's in play in the background, I'm not going to cover it too much here, but it is definitely something that you want to be aware of. So now to standardize those residuals, we could work both with either those Pearson, or we could work with the Deviance residuals. And so you'll notice here, both the standardized ones, I am denoting them with an R, and then the subscript tells you whether or not it is Pearson or Deviance. And then again, these are going to be both for the kth covariate pattern here. And you'll notice that they are just equal to their respective residual divided by the square root of 1 minus h. So just a couple comments here on residuals. So plots of residuals against the explanatory variables or linear predictor values may detect a lack of fit. When the fitted values are very small, the residuals tend to lose their relevance. When explanatory variables are continuous, it's common for nk to equal to 1. In this case, yk can only be equal to 0 or 1, and the Pearson residual can only equal 2 values. Caution needs to be taken about regarding either as extreme, and a single residual is usually uninformative. When data can be grouped into sets of observations having common predictor values, it's better to compute them for the group data rather than the individual subjects, and that's a typo there. Alright, so let's look at the goodness of fit test. So each of these types of residuals can be squared and added together to create a residual sum of square-like statistics. And so you can get one either for the Pearson residuals or the Deviance residuals. In practice, both of these statistics can be compared to a chi-squared n minus p distribution as a rough goodness of fit test. However, this test does not actually work very well. So several modifications have been proposed, including an early test proposed by Homer and Limshaw that remains popular and is available in SAS. Other better tests have been proposed as well. And so next we'll talk a little bit about some diagnostics. So you may recall that in linear regression there were a number of diagnostic measures based on the idea of leaving observation I out, refitting the model, and seeing how various things change. So in other words, residuals, coefficient estimates, fitted values, and so on. So for linear regression, it was not actually necessary to refit the model n times, so there are some shortcuts based on the projection matrix available. The same idea can be extended to GLM, although we can't take advantage of that explicit solutions shortcuts without making approximations. So the resulting approximate statistics are said to be one-step approximations to the true value. The issue is that we can quickly calculate the one-step approximations based on the current weights without refitting anything, but to calculate the exact value we would need to go through in iteratively squares algorithms. And so the approximations are usually pretty good, although if one point has a very large influence, then the approximations may be quite different from the true value. And so it ends up that these one-step approximations allow us to quickly calculate the following, and you'll notice that these are very similar to things that you saw in linear regression. And so I'm not going to spend too much time looking through these. I'm just going to mention them and let you read them on your own. But you could calculate variance inflation factors, which we've seen before. We can still look at multicollinearity between our explanatory variables. And then what I have here at the end is some example looking at that Donner-Parter data that we have seen before, and I go through leverage, Cook's distance, delta beta, and some residuals here for you to look at. So in summary, residuals are certainly less informative for logistic regression than they are for linear regression. Not only do yes-no outcomes inherently contain less information than continuous ones, but the fact that the adjusted response depends on the fit hampers our ability to use residuals as external checks on the model. This is mitigated in some extent, however, by the fact that we are also making fewer distributional assumptions in logistic regression, so there's no need to inspect residuals for, let's say, skewedness or heteroscedasticity. Nevertheless, issues of outliers or influential observation are just as relevant for logistic regression as they are for linear. So inspecting a plot of Cook's distance is usually wise. If influential observations are present, it may or may not be appropriate to change the model, but you should at least understand why some observations are so influential. Finally, keep in mind that although multicollinearity and variance inflation are important concepts, it's not always necessary to calculate VIF to assess them. It's usually a good idea when modeling to start with simple models and gradually add in complexity. If you add a variable or interaction, the standard errors increase dramatically, and this is a direct observation of the phenomena that VIFs are attempting to estimate. Now here at the end, I do have the code for you to create all of those plots in R and in SAS. And I have a note here that the kind of the fancy plots that you're going to look at on your own up there for the Donner Party example, those were created by a faculty member who previously taught the course using custom code. You don't actually have to use custom code to make these. Remember, when we look at diagnostics, most of the time we don't need them to be pretty to go into a publication. It's just, we want to glance at them to basically to help evaluate our model when appropriate. And so here I have some code for you. This will create rougher plots, but you can still gain all of that information. And then if you're interested for your own knowledge, here is all the supplemental code to make those nice pretty plots that you see up in the notes. And then of course here's also how to do this. That should say in SAS. I'll fix that in your notes.